Ma'am, this is Brajesh here. Vibha was joining now.
Yeah. A very good morning to all the participants.
Good morning, ma'am.
Good morning, ma'am.
Yeah. Hope you enjoyed the session yesterday. Yesterday there was some disturbance in the morning session. Probably today you will enjoy better because yesterday it was only the introduction to robotics. But today you will be having more interesting, more insight into the electronics and the actual construction of the robo starts now. So I think you should be more attentive now and take more active participation in all the sessions from now on. Okay. Happy learning. Please take care. Yeah. Yeah, I hand over to the speaker now. Please, Brijesh, can continue. Hello?
One second, ma'am. I'm here.
Yeah. I think today the first session is basics of robotics, mechanics, and essential related topics by Vaibhav S. Kansal. We have introduced you yesterday about the partner speaker. So he'll be taking you today for the mechanical parts of the related how the robo is mechanically constructed. Then you will have the sessions with electrical and electronic components. Maybe today or tomorrow you will have more towards the programming concepts and future scopes of that you will be going through in the next sessions. Okay. Please, Vaibhav.
Yes, ma'am. I'm here. Just give me a minute. I'm just setting it up here. Ma'am, I'll take it from here. Thank you. Good morning, everybody. So today I'll be.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Yeah, good morning, ma'am. Just give me a minute. 1 second. I just have it up. I'm just opening my PPT. Okay, can you see the presentation? I'm presenting the screen.
Yes, sir. We can see.
Yes, sir.
Yes, sir. We can see the presentation.
So, yeah. Okay. So today I'll be teaching. Not teaching, but I'll be sharing what and all we do when a student has to take up robotics. So there are three areas of robotics, being mechanics, programming, and electronics. So the first thing that they will learn when they start with robotics, when anybody has to start with robotics, is we start them with the primary reason the understanding, because they can see it physically, they can see the motors running, they can see how the wheels are rotating. So there is some sort of a physical there is a feedback that they will get, and when they learn something and through observation they will understand. Electronics is something that we will introduce in the little later stages. Programming, basics of programming will start after at least 3 months of their starting with robotics. So the first and foremost thing that we do is, the mantra that we live by is knowing it and not doing it is yet to know. So whatever is the concept, we try to attach some sort of a model, some sort of an experiment, so that they understand the concept well. So that is what we believe. Do it yourself is where they understand the concept. So it is almost like you can keep talking about rainbows to a blind man, but he would understand all the intricacies and concepts. He would even answer any kind of quiz questions on rainbow, but he would not have really seen it. So if any kid has to know a concept, they have to experiment with it. So this is what we believe, and that is one of the reason why we start with mechanics. So in mechanics, we see mechanics as is a branch of physics. It is an applied science. Um, uh, Mechanics is just an area of physics where motion, force, and object is involved, and there is some cause and effect to it. So this you can easily observe, understand by just looking at it and doing some experiments and trials with it. And hands-on approach will ensure the learning of basics mechanics is taken care of. So you can start, even for a third grader or a fourth grader, you can start designing curriculum in such a way you introduce mechanics with simple experiments. So these simple experiments are nothing but beam robotics, beam bots. So beam bots stands for biology, electronics, aesthetics, and mechanics. So these resemble robots, but they are not exactly robots, because this is the 0th stage of a robot. So this is not yet a robot. If you put in some programming aspect to it, then some more electronic concepts to it, it becomes a full-fledged robot. But this is right now, this beam bot is something that resembles some sort of a robot. You see this image. So this we don't even know what it looks like, but you can clearly say, oh, this is something that could be a robot, right? So that is beam robotics. For us to understand few key concepts like center of gravity, motion, force, mass, acceleration, lever, things like gear ratio, pulley, speed of the motor, hydraulics, pneumatics, friction. So these are the concepts that one has to understand if they are trying to design a robot or build a robot. So if you are conducting a course wherein you want to build a robot for the kid, so they will build 3-4 models. If you don't understand any of these, say 1 or 2 concepts you miss out, then the robot might not be as rugged, or it won't perform in the way that you would want them to. So what we have seen is a half-baked kit. If the kit is not properly, the robot that we give to the kids, there are some mistakes in the kit. Then what happens? Mute them all.
આપણે તડકો નહીં આવતો એટલે ઘરે નહીં બનાવતી, મનીષા ભાભી મોકલે છે.
Yeah. So the robotic kits that you provide for your kids, right? When they enroll for your robotics, the robotic kits, if it has some problem, say even the nut and bolt, they are not fitting together. So you got to understand what is the pitch of the nut, what is the pitch of a bolt, and how these two things will match up. Unless you are buying a kit that is ready-made, like a Lego, or from a company similar to Lego, then you can be assured that, okay, whatever I build, it will work. But if not, you have to know these concepts before you even design a robot. So today we will do a little bit of hands-on on Tinkercad, then we'll jump to as possible in terms of center of gravity, force, the little dynamics and the mechanics involved in building a robot. Okay, so when we start with mechanics, we have what we have understood, for a little younger kids, say 3rd, 4th standard, or even 5th standard, they have a very keen sense of observation. You show them, they'll be able to tell you and why something will not work. Just that they will not know the terminology. They will not know. And when you want to get into an advanced topic or a subject, without the key terminologies, without understanding few basic concepts, it will be very difficult to understand or jump to the complex and higher level concepts. So it is very important to understand the core fundamentals and the terminologies before getting a head start. So can anyone tell me what is the difference between the force and pressure?
Pressure is basically force applied on an area.
Anyone who wants to answer?
Unit area.
Correct. So force applied on a unit area. So for this, I usually ask a student to do this, just to blow on my hand, say like this. Then you're applying some force on this much area. So this becomes pressure. There is a pressure exerted now. So, and this is how you can, with very little things that you can explain the difference between these core concepts. And taking forward the same pressure and the force thing, we give them two syringes with one tube attached, and we make them build this, okay? And when they press this one side, the other side extends, and we'll ask them why this is happening. So it is more of observational and learning rather than you telling why this is working. Instead of getting into the Archimedes principle, the laws of fluid mechanics, we tell them why this is happening. So they will understand. They'll have this observation that tells them. So you are pressure, so extends and all of that. So what is the pressure? What is positive pressure? What is negative pressure? What is the suction pressure? So they'll understand, and we will tell them this is a basic pneumatic system. We have now built the basic actuator. So we can say an actuator because input is on one syringe, and you can see a cause and effect the other syringe. So you press on one syringe, the other extending. This become a mechanism. See, what is mechanism? Mechanism has motion and force. There is some linking between these two concepts, right? So we can call this a pneumatic system, a mechanism, basic mechanism that is doing actuation, because there is some cause, you are exerting some force, and it is causing an effect. So these two bodies are connected somehow. So it becomes a mechanism. So and we would ask them how much force exerting. You are putting some force, and it is exerting not the same amount of force. But if you want to increase the force, you have to fill the syringes with liquid, say water or oil or something. So we ask them to fill it with a liquid. So then when you press, the movement is much more, the movement gets translated faster. The air was getting compressed and it was not so, responsive. Now the movement is faster. It is almost like instantaneous. You apply little movement here on one end of the syringe, the other end of the syringe, you can very quickly. This because the liquids are in. So now you can actually deviate from the topic and teach them about, in the science class, they would have learned what is an atom molecule structure, how they are arranged, in a liquid, how it is. So you can deviate from that subject. You can even speak about such things. Or if you want to, if you are running low on time, you just, come back to the applied science, because in your science class, you will be teaching what is friction. But in robotics class, when you want to teach friction, you will give them a context. It is almost like implication of friction on a robot. We talk everything that is related to the physics, but in terms of how it will affect the robot. That is how they can do trial error and find out what is better. Now that they have built this pneumatic system or hydraulic system, they kind of know what is better and now there should be an exercise wherein they have to find out what are the real life examples that they will find out which are the hydraulic systems are. So we show them pictures of a JCB or an excavator. So they'll know how these two links are moving, why this would have a certain particular way of moving, and why there is so much pressure, how they achieved so much pressure, and how they could excavate such heavy objects and how they are able to generate that much force. So this we are also connecting with how our muscles work and why movements are possible. We can even talk about joints, different kinds of joints, revolute joint, sliders, rack and pinion, all those mechanisms also we can speak, provided you have time with those kits. So if not, then you just stick to the basic actuator. See, I'm giving you context as to what works in a classroom when you want to start teaching robotics. So this is something that we have understood. Okay, if you teach like this, then they'll understand these concepts. Before getting into the inverse kinematics equations of building a robotic arm and executing a robotic arm. So since they've built this hydraulic system, now you can ask them for an application. They would come up with the first thing that they would say is a hydraulic jack or a jack. It is used in the cars and the garages. The other thing that they would tell is an excavator. So we would try to build this excavator. So they will assemble this kind of thing with these syringes. And now you can ask them to pick and place something, and they will find out how much pressure it can or how much force it can generate, how much weight it can lift. So these things are learned experientially. Okay, now that they object, we different kinds of force, and we ask them to define what is force. And we basically tell force is the cause that causes a motion. It is the cause for a motion. And we ask them to categorize different forces. So you are turning on a switch, you are pushing on a switch. So what is that kind of a force? So is it a push force or it is a pull force? So we ask them to categorize on different kinds of force: push force, pulling force, impact force, stopping force, deforming force. And there are other kinds of forces with different elements that will come in. Okay, and then we kind of tell what is the net force on an object. So we kind of want to free body and the free body diagram, and what are the forces that are acting on a robot. If my robot has to go straight or on an inclined plane, what are the forces that will act on the robot? Before getting to that point, we have to establish that there are multiple forces that can act on a robot. So the net force acting on a robot would be resultant of all the forces that are there. And if there is one force, mic is not audible. Hello, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir, you're audible.
Yes, sir. So very much receiving.
It is audible. Yeah. Yeah, so we are now telling them there are forces acting on a body. So now you can even talk about gravity. If they have not known, if they don't know what is gravity, you can even establish the fact that everything under the sun has a gravitational pull, and you can even establish the concepts of gravity. And then with some examples, you tell them what is the net force. Why do you add the forces? When do you subtract the force? And what is the balanced and unbalanced force? And you tell them if an object is in rest, it is a balanced force. If an object it means which resulted the object to be in motion. Okay, so in this example, we are saying the two people are pulling a dog, right? So the forces, the dog is resisting that force. So there is three forces that is there on the rope. One is from the girl, the other one is from that boy, and there's a third force that is a dog. If all the three forces are, balanced, then the rope would appear to be stationary, right? And if it is an unbalanced force, say like in the seesaw or teeter-totter, what happens is there's an elephant sitting on one side, so the apple is jumping. Okay, it is now tossed in the air. Why does this happen? Because the weight is not balanced and it causes force, and the apple is tossed in the air. And now we are looking the same identical twins playing the seesaw, and they are kind of balanced. The bar is in level. I mean, there is no movement that is happening. So we can tell in object that is stationary, there is the resultant force of acting on that object is 0. If the object is in motion, which means there is one force that it was a turn force that body, and it set that object in motion. Only then laws, before explaining the laws, we have given fundamentals like what object has some weight. So these are the things that we would have understood examples, right? Object level balance. So now we can will state law before making them all of that.
Sir, your voice is breaking.
Hello, can you see my presentation? My Zoom had dropped.
Yes, sir.
Yeah, yes, sir, we can see.
It's very much visible.
Okay. Okay. Now that we have established the laws, I guess all of you understand or know what are the laws of motion. I don't have to go in depth into these things, right?
Yes, yes.
Yes. So now
Yes.
that we have stated what are the different
Yes,
laws of
sir.
motion, yeah. Now we understand for any object to be in motion, we need the constant supply of more and more force, because we need more force to keep an object in motion. We would have also thought about friction and how force diminish over time. So now that we want a motor to be working or a force to be in continuous, we will talk about motor. So the first example that I would take is of a ceiling fan. I'll just ask them to look straight up. There'll be a fan that will be rotating, and I'll ask them, can you put your finger into the fan? They'll be saying, no sir, and all of that. So you would understand that they have understood that there is some force that will be exerted on their finger, right? So you tell them that, and then you can continue with saying, see, the motor is simply rotating continuously. Can we use this on our robot so that the robot moves? So this is the robot that they build in the first year. Okay. All the components would be given, but before getting to the components and identifying the components, we would tell them what are the different motors that are available in the market and how they can buy these things on their own, because uh, this is something that will come in handy when they have to build their own robot or design their own kit. So what are the different motors that are available? We have this yellow color BO motor, which is the cheapest and the most used motor in any DIY kit. And we have base motor. We call this a simple DC motor. This yellow color motor comes in 15 RPM, 10 RPM, 45 RPM, 60 RPM, 100, 200, 150, 300 RPM, 500, 1000. Whereas these motors, the RPM varies from 800 to 1500. So when you're doing a project with these motors, base motors, it is difficult to control the speed. The same case with this base motor. This is the motor that will go into this yellow color gearbox. Okay. The other, if you want more torque, there is another motor called DC motor. This will cost about 250, 300 rupees in the market. So DC motor are little more, they can take little more torque. It operates at a little higher voltage. You would need a bigger battery. The same case with BO motor, it works at 6 volts to about 20 volts you can give to this yellow color motor. Then we have stepper motor. Stepper motor requires a programming board and a motor driver because it has 4 terminals. Stepper motor will have 4 to 5 terminals sometimes. Okay.
Sir, what is this yellow color, sir, motor called as?
It is battery operated motor, BO motor.
Battery operated motor?
BO motor. It is battery operated motor. In short, it is BO motor. It is very popular.
Thank you, sir.
Okay. So the BO motor that you buy in the market will not come with the wire terminals attached to it. You have to solder the wires into the motor, or you have to ask the vendor to do it for you. Okay. The same case with any motor. Sometimes you don't get the motors readily with the wire terminals. So that is something that you have to take care of, how you give the motors and how
do we have a vibration motor as well, which we use for the mobile phones?
Vibration motors, I have not put the photo here, but the motor that you see with the blue and red terminal on the right is something that you can use to do it. Just that on the shaft, what you can do is, what we have done is, instead of buying a vibration motor which has an offset weight attached to it already, we gave them some part of the clay. We give them some clay and they will put it there. When they unbalance the clay, they mold it in a different shape. The entire system, when rotated, when it is spun, and you can see the vibration is created. So you can make a bristle bar. So that is something that you make them do, bristle bar. Or you attach some sketch pens. You would have seen some videos. Then you can make that drawing machine. So drawing robot, you can call it something. So these are all the beam bots that you eventually make them do in your session. Then you have servo motor. Servo motor rotates in a particular angle, say 0 to 180 or 220. So there is a particular, there are servo motors which rotates continuously, like continuously rotation, like a BO motor. But servo motor again comes with 3 terminals, 5 volts, ground, and the signal pin. Signal pin requires a PWM signal. It's an on-off signal that can be generated from a programmable board. So we will look into some of the demos in the coming session when we do the Arduino session, right? So right now I'm just giving you the option and the selection for the motors, what and all you can choose. If you are building a fan cart wherein you have to attach a propeller and you have to spin it very fast, so this base motor is something that you can use. And this is a drone motor. This is a brushless DC motor. This requires an electronic speed controller, ESC, and it also requires the battery required for this is little expensive, and that is why drone workshops or drones are little expensive, the DIY drone kits. Okay, and if you are mentoring your students for a sumo wrestling robot or an all-terrain robot where torque requirement is more, there is something called as RS motor, which I put in the left bottom corner. So RS motor is something that will cost about 400-500 rupees in the market, and this requires a huge current, and this probably you have to use a relay or a motor driver which will give at least 2 ampere current. So when choosing a motor, these are the few parameters that you have to keep in mind before you select a motor for anything. In the class, when we are teaching about the subject called motor, because now that we have established the requirement for a motor, in the class, what we make them do is we provide them with bare copper wires and magnets and batteries, so they build their own motor. So there are DIY experiments in the that's available in YouTube, wherein you ask them to build the motor themselves, and once they see something that is rotating, then they will appreciate what are the different parameters of a robot. I mean the motor, right? So the first and foremost thing is the price, whether the motor is affordable for your project or not. The second thing is how fast you want the motor to rotate, and how much weight it has to pull, and whether your motor can be attached to the wheels, and how would you attach this motor to the body of the robot. See, these motors, everything, like every motor has a different mounting holes. Mounting holes is the holes that you use to attach a motor to a body. So there are different clamps that are available for each of these motors. So motor selection, you have to understand what are the current consumption for each of these motors, and whether you have a driver or a board or a programmable board that is compatible with the motor. And then now that you understand these parameters, the next thing is, what is it that you want your kids to build? I think you got to have a problem statement before start designing a robot. Why are you building this robot? What are the parameters you want to tackle? Whether you want your robot to go on an inclined surface, how much inclination, how much weight the robot should carry, or the robot itself should weigh. Is there any upper limit? What are the number of wheels, number of motors that you want the robot to have? So these are the problem statements that you got to have before designing your own kit. So here we have used 2 motors, 2 wheels with 1 caster wheel. So this is like an auto configuration, like you would see in auto rickshaw. So that kind of a configuration where the contact polygon is a triangle. Contact polygon is the contact it is making with the ground. So that is a triangle, and the most of the weight, the center of gravity, has to be within the contact polygon for the robot to be stable. So I'll cover that thing again later. So you got to have what is the problem statement. Once you know what is the problem statement, say I need to build a robot with 4 wheels, 4 motors, then how much speed or how much distance it has to travel. Suppose you are mentoring a team for a robo race or a sumo wrestling robot. What should be the speed of your robot? This becomes very critical. Say you know the track length is like 20 feet, and you have to reach the end line within the shortest period of time. So you would know what is the distance that it has to cover, and if you have a target in mind, I want to cover the end goal within this stipulated time, then you kind of you know how to calculate the speed, I mean the desired speed of the robot. And to find out the desired speed of the robot, you got to have a wheel, and you have to know what is the radius and diameter of the wheel. So using this formula, speed is equal to circumference into RPM. RPM is rotations per minute. So the speed that you get will be, if we are measuring circumference in centimeters, so the speed will be centimeter per minute. So if you use this formula, circumference if you find out, or radius if you find out in centimeter, it will be centimeter per minute. If the radius you are finding it in millimeters, it will be millimeters per minute. RPM is the rotations per minute. When I say RPM, it is rotations per minute. You have chosen a motor, and you have selected the RPM. Okay. So you get, say if you're buying a bio motor, you know what is the RPM. If you're buying a servo motor, you can control the speed and angle of rotation. If you're buying a drone motor, you would know this will rotate at 10,000 to 30,000 RPM. So RPM is something that you will know from a manufacturer, or you can even with a stopwatch, you can calculate what is the RPM. So once you know the RPM and the circumference, or if not circumference, use this formula 2 pi r. Or if you don't know the circumference, just know the diameter, then do this formula pi d. So you will know the speed of the robot. So now that you know the speed of the robot, you can ask students, or you can even calculate. Say that there will be problem statements wherein you have to push a block of something, and they would mention a block will not weigh not more than 1 kg or 2 kg. Then you have to know how much force your robot has to exert. Okay. So
Sorry to intervene, sir. Sorry to
yeah, please
intervene.
tell me.
But the circumference and the diameter that we're talking about, is it the diameter of the axle that we are taking in the motor?
No, it's the wheel of the wheel. The
Okay.
wheel that goes with the motor.
Understood.
Yeah. So see, for this, there's another concept called torque. I'll come to it again. Again, I'll answer to this question: why we have taken the wheel and not the axle of the motor? Because axle of the motor will be just 1 mm, and no matter what the calculation it is, it will remain the same, right? So, but when you put a bigger wheel, the robot tends to go faster.
So is it like the system of the gear that we are going to put into the axle of the motor, which is going to create the difference?
Okay, so here, no. So here, when you buy a motor, if you are buying this base motor, the gray color one, can you see the mouse pointer also when I'm sharing?
Yes,
this?
sir.
Yeah. So this gear, when you buy, this is called a base motor. You can only control the RPM with giving more current and voltage to the battery. But in our robots, we use this kind of a battery where there is no voltage control. So RPM of this motor remains constant, say 1000 RPM. So this is in order of 1000 to 2000 RPM, these base motors. But this is the same motor that you can see here. This is the same motor actually. Okay. And this yellow color part is the gearbox. It has a reduction gear system. It will convert this 1000 to 2000 RPMs to 100 RPM. So when you buy this bio motor, you have to ask for a bio motor which is 100 RPM. So you will know, okay, this is the RPM that you will get. You can expect a 10% tolerance, which means your motor could, if you are buying a 100 RPM motor, you might end up getting a motor plus or minus 10 rotations per minute. Okay. And usually these motors are not balanced. So because of the physical constraints and the friction within the gears, these are not the same. When you buy two of these motors, not the two identical motors, you might not get.
Okay.
So now we are done with the speed calculation. And now there is a block of wood or something that you have to push. So what is the force that is required to push the block of wood? So for these reasons, we are using Newton's law, F is equal to ma, right? So if it has to go and hit the wood, and the wood has to move, it has to, which means the robot will come with its full speed and it will hit. Considering what is the minimum force we want, we will consider that robot comes and it just hits the wall and it stops, which means the robot will come to a halt. So acceleration is change of velocity, or the rate of change of speed, which the robot was coming at full speed, now it stopped, right? Now we found out what was the speed. Now we know the robot has attained that speed when it hits the wall or the block of wood. What is the change of speed divided by time? Okay, then you get acceleration. Then you multiply with the mass of the robot, you get the force the robot would exert on the wall. Okay, so the F is equal to ma is something that we do after we have built the robot and we put it in some kind of an experiment. We increase the robot mass by adding more things or keeping more objects onto the robot. And then we see how the motor also struggles to pull the robot. So it becomes difficult for the robot to move around, right? So we tell them this is because you need more force. Now your mass is increasing, which means you need more force. And your motor is not giving more and more force every time because you're not increasing the voltage battery. So you give reasons. You will get lots of questions like this. I think, I mean, when you're doing this kind of concept, if you understand these equations, if you understand the basic, you'll be in a better position to explain their answers. So talking about the torque. Torque is the rotational force. Because we put more weight, now they know they need more force. But when the object is in motion, in a rotational motion, you don't call it force, you call it torque. Torque is the rotational force of the body, the rotational force, the force that will make an object rotate. So any body would rotate only when there is a pivot. Pivot means it rotates about that axis. So you apply a force on the body, then it tends to move. So I'm applying force on this wrench. So I'm able to rotate that nut, right? So the center of that nut becomes the pivot about which the wrench will rotate. So about which the wrench will rotate. So I'm considering the center of the nut when you're doing the nut bolt thing. Center of the nut to be the pivot, and from there you're applying force, you're holding it and doing it, and there is some distance in between. So what is that distance? That is d. So what is the force you're applying? That is F. So torque is T, which is force into distance. So distance, the force is always perpendicular to this distance. Now they will understand, okay, you need more force. Why they are telling force instead of torque? Because you see in the specification, you just Google what is the torque specification of a BO motor. You will see it is, yesterday in one of the slides, I just showed what are the different specification of a motor. Torque specification and RPM. That's why I didn't include it in this slide. So you would get those calculations, and you can easily find out what is the force and the distance. So distance, when it is a rotational body, now that you have connected the wheel, the rotational body is the entire wheel itself, and there is a contact to the surface. So right, and the wheel, when it rotates, it exerts force on the ground so that the robot propels or it moves forward. So which means essentially the force, the point of action of force is the ground. So I'll just use this. So if this is the wheel and this is the ground, the point where the force acts is the contact surface of the ground, and this is the axle. The center point of the circle is the axle of the motor. So you consider radius. You consider radius of the wheel to find out what are the torque required. And torque of a motor is usually, per centimeter. They say 5 Newton meter, so something like that, or 5 kg centimeter. So in 1 centimeter, this robot can pull 5 kgs. So you can ask them to do a pulley experiment. You just take one motor and tie a rope around it, or put one pulley and then do a rope around it, and then on the other end of the rope you attach one weight. Now you ask the motor to rotate. You keep increasing the motor to find out what is the torque that is being generated or exerted by the motor. So we can conduct those kind of experiments. We do those pulley experiments. We do a bristle bar with the vibration motor. We tell them how offset is bad and why wheel balancing is done. Then there are simple machines where we teach them pulley. Obviously, nut, bolt, screw is something that we would have given so they understand. Lever is where they understand. So yeah, so the first and foremost thing that we teach in simple machine is the lever. Lever is something, it is a balance, right? So you put two objects and it starts balancing. And how you can leverage by applying little force, you can generate more force. So the fulcrum and the more weight and less weight scenario, how you can amplify the force and effect with little thing. Once they know how you can amplify, you can now ask them, if I have to increase the speed of the motor or increase the torque of the motor, what do I do? So we have a gearbox that we give them with lots of gears that they can plug and then rotate one gear and all the other gears rotate. So this gearbox is something that we give when they have understood what is lever and how you can amplify force and things. So now, one second. So now that they can know how to amplify force and cause and effect that they can influence on, we take them to, we ask them question, can you increase the RPM? Can you decrease the RPM? Can you increase the torque of a given motor? Now we tell them about a gear system wherein a motor is connected to a gear and another gear, and to that other gear you connect a wheel. Now you tell them what is this gear. So you can tell this is the teeth, this is the axle of the gear, and what is the meshing of these two gears. And when the two gears mesh, which is the driver gear and which is the driven gear. So driver gear is where you put it is the input. Driven gear is the output, the load. Okay, wheel is the load, and effort is done by the motor. So gear is nothing but two wheels that are like meshing together. So one will cause the other one to rotate. So the proper meshing, too loose, too tight. So how the meshing has to happen? When the two gears are pressed against each other like this, you will see lot of friction. When they're loosely held, they might lose on one or two teeth, and it might start spinning freely. So proper meshing is required. And once the meshing has happened, you provide effort to one of the gears, the other starts rotating. So these are the gearbox experiments that we do, and we ask them to calculate the number of rotations the driver gear is doing when the driven gear is rotating some 100 times. So we tell them what is the gear ratio. When you're using two gears of the same size, then you don't have any problem. But when you're using gears of two different sizes in terms of number of teeth, there is a gear ratio. So there are two things, gear reduction and gear overdrive. When you're using a smaller gear to drive a bigger gear, what is happening? You are rotating more times here, and the number of rotation has been reduced. So you can the relation here is the speed and torque. When the speed decreases or the RPM decreases, the torque increases. When the torque decreases, RPM will increase by this equation. So with this equation, you can find out what are the number of teeth in driver gear, driven gear, and find out what is the gear ratio. Then there are different types of gears: spur gear, helical gear, bevel gears, worm gear, rack and pinion. So we saw this arrangement, right? So here the two axles, the shaft of the motor and the axle of the wheel, they were in the same plane. They were parallel to each other. If they are parallel, you use spur gear, and spur gear makes a lot of noise and there is more friction. And if the engagement has to be smooth and silent, you go for helical gear. The shafts are still parallel to each other. Bevel gears, the shafts are 90 degrees to each other. If you want to keep the motor like this and wheel like this, right, then you can use spur gear. If you want to keep like this, the motor is like this and the wheel is like this because of the arrangement, then use a bevel gear system. Rack and pinion is required when there is some linear actuation required. Linear actuation in terms of you want to hit something, or you want to turn on a switch or a reset button. You just rotate the motor and the rack will go front and back. So the rotational to linear motion is achieved. Worm gear. So you have a robotic arm like this, and you have a spur gear. So what happens is the robotic arm, because of the torque, even when it is in off condition, it has to stay there. If you have worm gear, the reduction is so high that it almost seems like the only effort can make the driven gear rotate. So here the gear reduction is too much. And also observe how the axle and the axles are in perpendicular directions in a different plane altogether. So now that they have understood how to reduce and all of that, we look at different mechanisms. So one such thing is a walking mechanism. Now that they know how a DC motor works, by this point, to observe all this gear, the easy option is to break open the BO motor that you have. So you give one extra BO motor to the class. So one extra BO motor, which will add about 50-100 rupees to your project. Let them break open this gearbox. There are just there are two nuts and bolts. If you remove, the entire gear breaks open, and you can see all of these gears. Not all of these gears. You can see bevel gears, worm gear, and spur gear. And then once you have broken open the motor and the gearbox, they know how the gear reduction is happening. And now you can get them doing some sort of a mechanism. Say rack and pinion, you did rotational to linear. So then you can ask them to build this kind of a robot, a walking mechanism. And you can talk about the walking dynamics. So when you're walking, what are the ground contact points at each stance? Say right foot forward, from there to you are taking one step, and then again you're coming back to the right foot forward. So there is some ground contact at each stage, right? Then you can talk about the stability, static stability, dynamic stability. All these terminologies you will use if they are 5th and 6th standard or 7th standard and they're starting off with robotics. If they are doing in 4th standard or 3rd standard, you don't teach them about stability and ground stability. Rather, you just ask them to build this robot and they will find out why this is not standing properly, what I should have done so that it stands properly.
So I'm turning it for you.
Okay. So the walk cycle. So walk cycle is that period wherein you are taking stride and from right foot forward to left foot forward, and then you are again coming back to the right foot forward. What are the different stages and what are the ground contact points? These are required so that they will know what are the contact points and how you are balancing yourself at each stage. So there is something called a static stability and dynamic stability. When you're standing, right? You're able to stand. The robot also has to stand. Be it a robot, a remote controlled robot, or a car that you saw, or a walking robot like this. Even when it is in off state and the motors are not running, it has to stand. That is static stability. Dynamic stability is when the motor is on, when the robot is moving, whether it is able to stand on its own. That is the dynamic stability. For the stability to happen, there should be more ground contact. If the ground contact is more, then the stability, static and dynamic, will happen naturally. If the ground contact is less, okay, in human beings, for the body and the weight ratio and how tall we stand, the contact to the ground is very less. But we have a control system with the ears and the brain. We can control our muscles and we can balance ourselves. But a robot doesn't have any of those neural system, right? That is the reason why you see the base of the robot is so big. The leg is made so huge. So when you're designing the robot, just keep those things in mind. If you're bringing in a control system and an algorithm that can balance itself, then great. The contact surface could be less. If not, your arrangement of wheels, motors, or the legs or the leg mechanism should be in such a way that the contact surface is more. And what is the surface that you are in contact with? That is environment or the surface that you are in contact with. These are the three factors that you have to first consider or ask yourself when you are going with the walking robots or any robot which is moving. So the basic thing that you can do is when it comes to contact point is there are 3 contact points here. the toe and the heel of the right leg. So you can draw one rectangle, you can, you can draw a triangle. This is a contact polygon. So when a stool or a tripod is kept on the ground, there are 3 contact points, and you can draw a triangle from the 3 contact points. And if the center of gravity of that system is falling, the projection of that system is somewhere here in the middle, but it is falling right within the contact polygon, right? It is in the center, which means this tripod, this bench is balanced. It has good static stability. Even if you sit on it, you will not fall. But you see the legs are bent inwards. Static stability is great in this case because the center of gravity is still within the contact polygon. But the moment you sit on the little edge of the seat, then you will definitely fall. You will take a fall because the center of gravity with you sitting will be outside this contact polygon. So you will tip over. This is another unrealistic bench where the contact polygon is outside the normal center of gravity of this bench. So this bench will never stand still. When you want to set it straight, it keeps falling because the contact polygon and the center of gravity is not falling within itself. The center of gravity is not within the contact polygon. So this you have to explain when they build this robots or the walking mechanism. What are the contacts that it is making with the surface, and whether the center of gravity of this system is within the contact polygon that it traces. You have any questions so far? Hello, anybody has any questions?
No, it's fine.
Yes, sir.
Yeah.
Do we also check the treads of the wheels when we go for finding out which kind
Correct,
of
ma'am.
wheels
Yes.
are required?
Correct. So that's the next topic. But when we are going for a wheeled robot, see, we have understood with the movement of this thing, when the motor is continuously rotating, but with each rotation, it is only taking one step or half a step based on the mechanism that it uses. Okay, it will not, with one full rotation of a motor, you will not have achieved one full walk cycle with one of the mechanisms here, right? With a wheeled robot, one rotation of the motor will result in one full walk cycle, or it is more efficient. Okay, so it is more efficient when it comes to wheeled robot, and it is easier to construct. The control system and the number of motors, linkages, moving parts are less. You just have to put the motors and the wheels together and have one chassis, then you will get it. So there are different wheel configuration that you see. This depends on what is the friction that you want, what are the surfaces that your robot has to go. So there are competition called robo races, all-terrain vehicles, soccer robot, sumo robot, right? The friction required or the grip required in each of these cases are different. If you are building an autonomous line following robot, the friction required is very minimal. If the robot is able to just move, that's enough traction for the robot to have. And you don't have to go with the wider wheels. So you can go with a very thin wheel also for line following robot. And if you're going for an all-terrain vehicle, the track or the skid belts or the track belts, this becomes important. If you're navigating with,
go to the channel Teams.
Yeah.
Another.
If your robot has to navigate within the tight spaces, then there are other wheels, the special wheels like mecanum wheels or omnidirectional wheels. You can use those, and if you can build a steering mechanism, you can have a steering mechanism and have one servo motor to control the steering mechanism. So depending on the wheels, your robot will have different capability. That's the same case with the chassis. There are multiple materials that you can choose from. You can ask them if I have to hold these two motors together and these two wheels together to build a robot, what are the different materials that they can go for? Should they go for plywood? Should they go for aluminum, metal? What are the different options that are available? And can you work with these materials? Can you cut these materials? Can you attach few materials and things like that? So what happens is the chassis becomes a very crucial part because it tells what will be the wheelbase. Wheelbase is the distance between the two wheels or the width of the robot in most cases. So the chassis will tell what is the wheelbase, what is the ground clearance, how the robot is constructed, whether it has a suspension mechanism or not, how many motors you can connect. So chassis is like the skeleton of the robot, and you can talk about the strength of the material, choice of the material, kinds of manufacturing that you have to go and you have to build these kind of chassis. So out of these, I see a lot of these things are laser cut, aluminum, acrylic, very basic ones, but they are able to build a chassis. Okay, there's one question. The example which you gave is DC motor and how it will rotate DC, how it will be used in walking robot here. Okay, I'll just take this one question. So here we have this motor and it is almost like a cycle pedal. You consider this as a cycle pedal. You would have seen a similar mechanism in a railway engine. Okay, a 360 motion is converted to a different elliptical motion, which enables the robot to walk. That is the same mechanism that is used here. So there is an offset here. The rotation is now transferred to an offset, and then it is almost like a mechanism of a train engine. That is how I'm converting the rotational motion to the walking mechanism. Okay, so this is about the robot and the chassis. We are running little low on time. Can we jump to Tinkercad? I'll consider what is a H bridge, DPDT, motor driver in the next class. I'll jump to I'll continue in the next mechanism class. Okay. So you have any questions so far with the basic concepts? I know I didn't cover much, but I'll cover DPDT and other mechanisms that are involved. That will ensure that you can build a sumo wrestling robot or a DPDT remote control robot. So in the part 2, we will learn what is that thing. So I'll just jump into Tinkercad, and tomorrow we'll look at Fusion, designing something in Fusion, 3D model something in Fusion, and then how we can laser cut or 3D print it. So today we'll just look at Tinkercad 3D modeling. You have any questions so far with the mechanisms?
I have a question.
Yeah, please tell me.
Sir, actually, I just read somewhere like the robot should at least have minimum 4 legs, right? So
okay.
Because for walking, at least one leg is in air because there's look at stability portion over there, right, sir? So when we're speaking about that 3 and center of mass coming at the center point, right, sir? So
Correct.
how do we explain that? I mean, I was just stuck to that point when explaining that.
Correct.
I couldn't move ahead actually after that.
Correct. So I'll tell you. So how we solved this problem when we built this robot. So when I designed this, when the offset was more. See, you see this offset. It is almost like cycle pedal. You are doing like this with the motor, and the front leg is getting lifted, and the robot is now the contact points are the 2 hind legs and the left leg. The right leg is in the air. So the robot was tipping over like this. How I solved this is by if I do annotations, I'll be able to
explain something in a polygon structure. So I was stuck
correct,
there
correct.
actually.
So yeah, so the contact points are this point, and now that the pedal has gone up like this, so the leg is in this formation. So this is floating in the air. This point is now here. Okay. So the contact points are these 3 points. So you get a very point like this, and the robot CG is here. Okay, so the robot will tip over. It will fall like this to its right. When the right forward leg is up, the CG of the robot falls in these 3 points being the contact polygons. The robot falls. So how I was able to solve this is I was able by increasing. Wait, I'll take a different color so it is okay. By increasing this width, by making the robot little wider, now I have this. By making it little wider, now I had this.
Increase the distance actually, right, sir?
Yeah, distance. So I increase the width of the robot so that the contact polygon falls somewhere very close. Even though it is outside, it was very close.
There is shift of center of mass then, sir.
Yeah,
There's
so
a shift of center of mass at that point.
yes, it got shifted. The center of mass from, so when it was at rest, it was a rectangle. The hind legs and the front legs, the center of mass was here. The moment the right leg was lifted, you had a contact polygon like this triangle, and the center of mass was here. So the robot was tipping over. By the time it was tipping over, what happens was this also gets lifted. The alternate legs, this also gets lifted. So the robot at some point, the contact polygon was not a polygon anymore, but it was just a line. It was just a line like this. So there are areas where the robot balances itself. So it is a mechanism, right? This doesn't have any controller or anything that will ensure the center of gravity is within the contact polygon. But it is a mechanism. It happens so fast. The time it requires to tilt and fall. Right. Yeah. So the time it requires. Yeah, it doesn't have any control. I hope I have answered your question.
Yeah, sir, I think this device is not at the same place as it is moving continuously. So
correct, exactly. So the contact polygon is evolving. From a square rectangle to a triangle, and then it is a line, and then the next contact polygon is shifted. So it is like this. I'll just show this how when it is moving, it is not in the same place. So the contact polygon was like this rectangle, and then when the leg was lifted, it was, this triangle. When it was lifted, then this was this line only, and the next contact polygon was this. Because the right leg is now stomped on the ground. Yeah, this is not there now. So you see the contact polygon pattern will be like this as it goes.
Right. Yes, sir, understood now. It is moving. I understood.
Yeah.
Thank you, sir. Thank you.
Okay.
Very nicely explained, sir.
Yeah, very nicely explained. In fact, the motion is very clear. The polygons changes shape. Thank you, sir.
Yeah,
thank you so much, sir. Thank you so much.
Okay. So this switching of the motor, how do you reverse and how you can explain it in class, and those things I'll explain in the next part. So I think we have to jump to the Tinkercad because we are running out of time. I'll just stop the screen sharing. I'll open Tinkercad. How much time I have? 5 minutes. 5 minutes. Huh? 10 minutes. All right. Okay, just go to Tinkercad.
IT.
सबमिट करने की हैं अभी आपके 2 सेक्शन बचे हैं
Just
So
go to
we need
Tinkercad.
to go to Tinkercad. We all need to go to Tinkercad.
No. You just look at, because we are running out of time, we could have done it hands-on. Usually in the class, what we do is we connect it to a projector or we show them how it is done. They all do it simultaneously. So the first time when you launch a Tinkercad, it will ask whether you want to log in or sign up. If you have not have an Autodesk account, you just please sign up. You can use your Facebook or a Gmail account. You can sign up very quickly. There are like few, this is an online, you don't have to install. You just have to go log in and then enter Tinkercad. So as soon as you enter Tinkercad, you will be guided through a lessons. So the lessons will ensure that you learn all of this. It starts from the basic. Okay, since I've gone through it already and we are running out of time, I'm just going directly into the design phase.
We need to do these on our own.
This you can figure out this, and if you're teaching kids from 3rd, 4th standard, only then you have to teach Tinkercad. Otherwise, we will look into another software called Autodesk Fusion. If you're teaching students from 6th standard, yeah, little advanced means you have to go with Fusion. This has lots of limitation. This is not a very, it's not a design software. It is actually made for kids to understand 3D space. It is for very young kids to get started.
Yes, we use Tinkercad for 3D printing.
Exactly, ma'am. Yeah. So to demonstrate 3D printer, to do something, some shapes very quickly, only then you will use a Tinkercad. And I thought we will build something and show few of the workspaces and what are the things. Since I'm running out of time, I have about 5 minutes time. I'll just tell you what is Tinkercad. If you go through the lessons that it prompts, no, then you will, anybody can figure out what it is. You have any doubts, you can reach out to me anytime. And this is a 3D workspace. This is a work plane. This is where you can add object with the middle mouse, the scroll button, the middle button in the mouse. You can scroll, zoom in and zoom out the workspace. Okay, when you press the middle mouse button and move the cursor around, you can move you can pan the workspace. Now you want to look at the workspace in different angle. You hover the mouse on this cube, which here on the left top corner. You just click and then you rotate. You can have a perspective change. Okay, okay. You can also use these zoom in, zoom out features. You can use this feature called orthographic and perspective view. In the perspective view, you will have the farther object will be smaller and the nearer object will be little bigger. But in the orthographic view, you will have this orthographic view where all the objects of the same size, irrespective of where they are placed from the viewer, it will all appear the same size. So when you're designing, go with the not the perspective view but the orthographic view. Okay, you can drag and drop any object onto the work plane. So you will see a lot of these anchor points, right? And you click those anchor points and move it around. You will get some shape. You will get some shape. And you can even reduce the height, you can reduce the width. If you want precisely how much you want, you just hover over this numbers, you click, you can edit the number. So exactly that you will get. Okay, I need some shape like this, you will get it. And you can even move it around. Just don't click on the anchor points, just move it around. You can move it around. How much you are moving also comes, you can change that, whether I'm moving in the Y plane, how much I'm moving. I want to move it 10 units, so it comes. So, or 100 units. Okay, so I'm moving this, then I'm changing the value. See, it is happening. Then you can always go back if you have done any mistake, undo, Control Z. You can even select it and delete, and it deletes. And then length is something that you can change from here also. Okay, you can add more shapes. And if the two shapes are intersecting and you have to select these two shapes, you can combine these shapes to form one shape. Okay, see now what it has become one shape. There are no two shapes now. It's become one shape. Now I want a hole in this. I just drag the cylinder, and I don't want the cylinder to be solid, but I want the cylinder to be a hole that the rectangle shape will have. So I will click the hole, and then I will select those things, and I will say combine. Now I have a hole in the object. Okay, now I can navigate. See, I have a hole in this object. By placing the shapes, there are different shapes. Now that I can simply place these shapes, I can build anything that I would want. There are other things like,
Sir, there is one thing that I want to ask.
yeah, please, ma'am.
Why are we learning Tinkercad in the robotics? Like, do we use it for designing purpose?
Yeah, so all this while when I was teaching mechanics, I was always teaching how you can plan your robotics mechanics course, right? How you could plan your mechanics design course. Now, the next session that I will take, I will teach you how to build a chassis, laser cutting, and 3D printing, so that you can fabricate your own kit and devise your own curriculum. That's been the objective. See, I'm not selling what I know. I want what are the skill set that you would want, so that you can design your own robots and curriculum and start teaching those things. And
understood, sir. Understood.
Okay. And in the classroom, so there is one topic that I'm taking, which is design thinking principle and 3D modeling. There I'll be telling you why exactly a student has to learn 3D modeling and why it is very essential. So in robotics, obviously we design a lot of robots using 3D modeling software. Without a 3D modeling software, you can't even conceptualize with the team and collaborate with the team. And hence the reason why we are learning 3D modeling. It is not just to do something. This is not a fun activity for the kids, but there is a learning which you want them to understand. Then there is animation and things like that, and simulation also. So I think my time is over here. Vijay sir? Over, or I still have time? Over. Okay. So you have any questions with the Tinkercad?
So before the question, you were telling something Lego, just to finish that said above that import point.
Correct. So now I want to export this thing, right? I want to export it. Why do I have to export it? I can 3D print it or laser cut it, or I just want to use this shape in a different software, where this could be an obstacle that I have designed in Tinkercad. I want to use it in a different 3D modeling software. I want to use this shape in a different software. So I can export it. So export has what are the different format that you can export. There's an object file, obj file, or stl file, or you can for laser cutting you do svg file. Okay, or you can, if you have a 3D printer connected, you can go to 3D printer and select which is the 3D printer that you are using. If not, if you have a different 3D printer, custom made 3D printer, export it as stl file or step file, object file, and then bring it into that environment and then create the 3D printing file. Okay, now I have something called as blocks. This has lots of curves. You would have seen some pixel effects. There is a very popular game and a movie called Minecraft, and kids are fascinated about such animated things. So now I've created a pixel effect onto this blocks. Right? If I have a 3D Lego bricks, now if I just press this thing, it will tell me what are the blocks that I have to put, which will closely resemble the shape that I built. If I want more resolution, even more resolution, it tells. So Tinkercad is used for kids so that they can build something. So they can visualize here and then they can build a Lego out of that. So that's about Tinkercad in terms of 3D modeling. If I had time, I would have started with Autodesk Fusion. Any other questions in the mechanics, or you had a different expectations, or something that you were expecting out of this session which was not covered, or you thought robotics was different? You can ask so that I will be able to address those things.
Participants, if you don't have any question, I thank Vaibhav on his detailed explanation on robotics with different how to select motors, the gear ratios, and how the actual machine works. Okay, so I thank Vaibhav for this session. Shall we break for 10-15 minutes so that we can join back at 11:15 again? Please join back at 11:15. Thank you, Vaibhav, for your very informative session.
Thank
I
you.
hope all the participants must have enjoyed the session. It's available in YouTube also. The live streaming is going on. The next session will have from Brijesh at 11:15, at 11:30. Basics of robotics. It is on electronics and essential. So Vaibhav spoke more on mechanical type. I think
Brijesh is taking
Brijesh
more
will
of
be speaking
electronics.
more
Yes.
on electronics components that will be associated with robots.
Correct.
I hope you are enjoying the sessions. We'll join.
Smell. Okay, thank you. Bye bye.
Now the session will start at 11:15 or 11:30.
11:30.
Okay, sir. Thank you.
Thank you.
Okay, sir. Thank you.
We have the next session at 11:30.
Next session is at
11:30 to 1 o'clock. Right? 1 to 2 is the break. We'll be joining back at 2 again. Okay?
Yeah.
Yeah. Thank you all.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.